Here you will see a list of 7 different properties of limits that will help us in evaluating limits down the road. Now, this list may seem intimidating at first, all right? But as we go through them, you might recognize these rules are not all that complicated. Our first rule, the sum or difference rule for limits. The limit as x approaches a of the sum or difference of f of x, that means f of x plus g of x, or f of x minus g of x, is equal to the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. In other words, if we are trying to evaluate the limit of a sum or difference, addition or subtraction, we can evaluate the limit of each component individually and then just add or subtract them. Rule number 2, the constant multiple rule. The limit as x approaches a of c times f of x, where c is a constant multiple, notice it's a number connected by multiplication here, is equal to c times the limit as x approaches a of f of x. In this case, what we are doing is we are taking this constant multiple and we are factoring it out from our limit. You guys by now are very comfortable with factoring out greatest common factors. This is just a factoring out a constant multiple. Our product rule for limits. The limit as x approaches a of the product of f of x and g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Again, this is saying if we are taking the limit of a product, we can evaluate the limit of each component individually and then multiply them together. We have a very similar rule for quotients. The limit as x approaches a of f of x divided by g of x, well, we can take the limit of the numerator of our quotient and divide by the limit of the denominator of our quotient. The power rule for limits. The limit as x approaches a of f of x raised to the nth power, well, the power rule says that we can evaluate the limit as x approaches a of f of x and then raise that quantity to the power afterwards. Our fractional power rule is very similar. The limit as x approaches a of f of x raised to the fractional power n divided by m is equal to the limit as x approaches a of f of x all raised to the n divided by m. Again, notice we are evaluating the limit of f of x first, and then we can raise it to the power, provided f of x is greater than or equal to 0, for x near a if m is even and n over m is reduced to lowest terms. What this is saying is that, well, fractional exponents, they give us roots, right? Raising to the 1/2 power is a square root. Raising to the 1/4 power would be a fourth root. And so if m is an even number, or we are taking an even root, well, then it has to be greater. Our limit must be greater than or equal to 0 because we cannot take an even root of a negative, right? That's what we are specifying here. And finally, our constant rule for limits. The limit as x approaches a of c, where c is a constant, is equal to that constant. All right, so what are a lot of these saying? Yeah, we can just break up our limits. We can evaluate the limits of each of the individual parts. Here, we can also factor out constant multiples from limits. Here, with powers, we can evaluate the limit of the inside and raise it to the power afterwards. And finally, the limit of a constant. Well, the limit of any constant will simply equal that constant. So a little bit intimidating at first, but the more you begin to use them, I think you'll become comfortable with what they actually mean. So let's get to some examples. Compute the following limits given that the limit of f of x as x approaches 1 is 8, the limit of g of x as x approaches 1 is 3, and the limit of h of x as x approaches 1 is 2. We are asked to find the limit as x approaches 1 of f of x divided by h of x. Well, notice that here we are dealing with a quotient. And our quotient property of limits tells us that we can evaluate the limit of the numerator and the limit of the denominator separately. In other words, I have the limit as x approaches 1 of f of x divided by the limit of h of x as x approaches 1. And this is good because we actually know each of these quantities. These are given values. The limit of f of x as x approaches 1 is 8. The limit of h of x as x approaches 1 is 2. Therefore, we have 8 divided by 2, which is equal to 4. Let's look at another one. The limit as x approaches 1 of 2 times h of x, notice that's a constant multiple, divided by g of x minus f of x. Well, separating this into all of the individual limits, we end up with 2 times the limit of h of x as x approaches 1, divided by the limit of g of x as x approaches 1, minus the limit of f of x as x approaches 1. So we're basically just taking the limit of all of the individual parts. And here with this 2, well, we pulled that constant multiple outside of the limit. And now we can replace each one of these quantities. We know that the limit of h of x as x approaches 1 is 2. We know that the limit of g of x as x approaches 1 is 3. And we know that the limit of f of x as x approaches 1 is 8. So we substitute those values in. We have 2 times 2 divided by 3 minus 8, leaving us with negative 4/5 as our final answer. Let's try another one. The limit as x approaches 1 of the cubed root of f of x times g of x plus 3. Well, roots, cubed roots, those are the same thing as fractional exponents. So we can rewrite this as being raised to the 1/3 exponent. And our fractional power rule says that we can actually evaluate the limit of the inside parts first and raise it to the 1/3 power, or take the cubed root afterwards. This gives us, and again, splitting up the parts of that are inside of our cubed root, we have the limit of f of x as x approaches 1, the limit of g of x as x approaches 1, plus the limit of 3 as x approaches 1. Well, the limit of f of x as x approaches 1, we know is 8. The limit of g of x as x approaches 1, that's 3. The limit of a constant, yes, 3 is a constant. That is just a number. This is going to be 3. Therefore, we end up with 8 times 3 plus 3 raised to the 1/3. 8 times 3, well, that's 24. Plus 3 is 27. 27 raised to the 1/3 power, or the cubed root of 27, is equal to 3. Let's try one more. Compute the following limits given that the limit of f of x as x approaches 5 equals -2, the limit of g of x as x approaches 5 is 5, and the limit of h of x as x approaches 5 is equal to 1. Our first one says the limit as x approaches 5 of g of x minus h of x divided by f of x. Well, what can we do? Evaluate the limit of each component individually. In other words, we have the limit of g of x minus the limit of h of x divided by the limit of f of x. Well, the limit as x approaches 5 of g of x, that's equal to 5, minus the limit as x approaches 5 of h of x, that's equal to 1. We have 5 minus 1 in the numerator, divided by the limit of f of x as x approaches 5 is -2. 5 minus 1 divided by -2, 4 divided by -2 gives us -2 for our final answer. The limit as x approaches 5 of the quantity g of x minus 3 times h of x squared. Well, notice that we have a power, and we know that using the power rule, we can evaluate the limits of the inside and raise to the power afterwards. We can also evaluate the limits of the individual parts of our inside, splitting it up into the limit of g of x as x approaches 5 minus 3 times the limit of h of x as x approaches 5. Notice we just factored out that constant multiple of 3 in front of the h of x. All of that being squared. Well, the limit of g of x is 5 minus 3 times the limit of h of x. The limit of h of x is 1. We have 5 minus 3 times 1 quantity squared. That gives us 2 squared, and 2 squared is equal to 4. One more here. The limit as x approaches 5 of 3 times h of x plus f of x. And notice right here, this 3 actually belongs to the entire quantity h of x plus f of x. All right, so a couple different ways you could consider thinking about this. Sure, you could absolutely distribute this 3 to both of these terms. Another option here is to factor out the 3 constant multiple from our limit to begin. Here, I have done that. 3 times the limit as x approaches 5 of h of x plus f of x. And now I can evaluate the limit of this sum by taking the limit of the pieces individually. This becomes 3 times the entire quantity, the limit as x approaches 5 of h of x, plus the limit as x approaches 5 of f of x. Well, what's the limit of h of x? That's going to be 1, plus the limit of f of x, that's negative 2. We have 3 times 1 plus a negative 2. 1 plus negative 2, well, that gives me negative 1 times 3 gives us negative 3 for our final answer. All right, so there we have some applications of using our properties of limits.